On one of the most isolated inhabited islands on Earth, hundreds of massive stone statues stand facing inland, their backs to the sea. These figures, known as Moai, were carved centuries ago on what we now call Easter Island or Rapa Nui. Each statue weighs anywhere from a few tons to well over 70, with some unfinished examples suggesting intended weights exceeding 100 tons. They were created without metal tools, without wheels, and without large domesticated animals for hauling. And yet, they were quarried, shaped, transported, and erected with surprising consistency. This is not a mystery in the sense of whether humans did it. Archaeology leaves little doubt that the Rapa Nui people themselves were responsible. The real question, and the one that has occupied researchers for decades, is how they managed it with the materials, energy, and social organization available to a small Polynesian society living on a resource-limited island. The statues were carved primarily from volcanic tuff, a relatively soft but cohesive rock formed from compressed ash. Most originate from a single quarry, Rapa Nui, where nearly half of all Moai remain partially carved into the bedrock, frozen mid-process. These unfinished statues act like a paused video, preserving tool marks, carving sequences, and design choices that allow archaeologists to reconstruct the workflow with unusual clarity. From a technical standpoint, the problem breaks into 4 linked challenges. First, quarrying. How stone tools made of basalt were used to carve multi-ton figures with controlled geometry. Second, finishing. How surfaces were smoothed, details refined, and weak points reinforced to prevent breakage. Third, transport. How statues were moved several kilometers across uneven terrain without wheels or draft animals. And finally, erection. How upright placement on ceremonial platforms, called ahu, was achieved with precision and stability. Early European observers assumed external intervention, imagining lost civilizations or visitors with advanced knowledge. Modern science has replaced speculation with experiment. Over the past 70 years, archaeologists, engineers, and physicists have tested competing hypotheses using full-scale replicas, friction measurements, structural analysis, and ethnographic comparison with other Polynesian societies. Many of these theories work, at least in principle, but each carries trade-offs in labor requirements, risk of statue failure, and ecological impact. Crucially, the Moai were not industrial products. They were cultural artifacts embedded in religion, status competition, and ancestor veneration. Their construction was likely episodic, communal, and ritualized rather than purely utilitarian. That means efficiency alone cannot explain their design. Symbolic considerations matter just as much as mechanical ones. In this series, we will examine the leading scientific theories one by one, not to crown a single winner, but to understand what each reveals about human ingenuity under constraint. The story of the Moai is not about lost technology. It is about how far careful planning, social coordination, and physics can go when applied patiently, over generations, by people who understood their land intimately. In the next segment, we begin where every Moai began, inside the volcanic slopes of Rapa Nui, with stone tools, muscle power, and a deep knowledge of rock. Nearly all of the Moai begin their lives in the same place, the inner slopes of Rapa Nui, a volcanic crater whose walls are composed of compacted ash known as tuff. From a geological perspective, this choice was deliberate. Volcanic tuff is soft enough to be shaped with stone tools, yet strong enough, when left thick in critical areas, to survive transport and long-term exposure once erected. The Rapa Nui did not carve statues as freestanding blocks. Instead, each Moai was sculpted directly from the bedrock, lying face up, and attached along its spine to the quarry wall. This method dramatically reduced early fracture risk. The surrounding rock supported the statue throughout most of the carving process, acting as a natural jig that prevented torsional stress while the form was still incomplete. Tool evidence found in and around the quarry shows extensive use of basalt picks, known as toki. Basalt is significantly harder than tuff, allowing repeated chipping without rapid tool failure. Where patterns on these tools and the scars they leave behind indicate a controlled, rhythmic carving technique rather than brute force hacking. Crews likely worked in coordinated teams, rotating tools and workers to maintain precision and reduce fatigue. From a structural standpoint, the carving sequence itself is revealing. The front of the statue, the face, torso, and arms, was completed first. Only after the front geometry was finalized did carvers begin to thin the sides and back. This preserved mass and stiffness during the most delicate phases of shaping. Even then, the back was left attached to the bedrock by a narrow keel, creating a hinge-like support that held the statue in place until the final release. Unfinished moai at Reino Raraku provide direct evidence of this workflow. Some are nearly complete except for the final undercut along the spine. Others show abrupt abandonment, possibly due to cracks, tool shortages, labor reallocation, or social disruption. Importantly, these unfinished statues vary in size, suggesting that experimentation and ambition increased over time as techniques improved. The statue's exaggerated features, large heads, thick brows, and elongated torsos, are not just stylistic. From an engineering perspective, they shift the center of mass upward and forward, which later becomes critical for transport and upright positioning. What appears symbolic is also mechanically advantageous, whether intentionally or through iterative tradition. Quarrying, then, was not the most mysterious part of moai construction. It was labor-intensive but technically straightforward, relying on rock mechanics, leverage, and patience rather than hidden knowledge. The true challenge began after the final cut, when a multi-ton statue, freshly freed from the mountain, had to be moved across the island without breaking. That problem, how to safely transition from quarry to landscape, is where theories begin to diverge sharply. In the next segment, we examine the moment of release and the first steps a moai took away from Reino Raraku. Once a moai's front and sides were complete, the most dangerous phase of construction began, separating the statue from the quarry wall and bringing it safely to the ground. This step represents a structural transition from a supported, semi-attached form to a fully independent mass, where failure would mean catastrophic breakage and the loss of months or years of labor. Archaeological evidence suggests the final detachment was performed gradually, not as a single dramatic cut. The narrow stone keel along the statue's back was thinned incrementally, likely over multiple work sessions. This slow approach minimized stress concentration and allowed the carvers to monitor cracking or deformation in real time. Basalt toki marks on the rear surfaces of unfinished statues indicate careful, shallow chipping rather than deep, forceful blows. Once nearly free, the statue could not simply fall. A controlled lowering system was required. Many researchers believe that earthen ramps or sloped fill were built beneath the statue's head and torso as it was carved. When the final connection was severed, the moai would slide or pivot gently onto this prepared surface rather than dropping vertically. The slope effectively converted vertical gravitational force into manageable horizontal motion. Soil analysis around Reino Raraku supports this idea. Sediment layers show evidence of artificial terracing and compacted surfaces inconsistent with natural erosion alone. These features would have served both as working platforms and as safety buffers during release. In some cases, statues appear to have been lowered directly into shallow pits, allowing them to come to rest upright or near upright immediately after detachment. Crucially, the statue's proportions again play a role. The thick head and forward-weighted mass mean that, when tilted slightly, gravity naturally pulls the moai face down rather than onto its back. This reduces tensile stress along the spine, which is the most vulnerable region once the keel is removed. In structural terms, the moai behaves more like a leaning column than a falling slab. Several statues found lying face down along ancient roads may represent failures at this stage or deliberate test cases. Fracture patterns on these fallen moai often show breakage at the neck or base, consistent with rotational impact rather than blunt collapse. This suggests that early builders were learning, adjusting angles, ramp lengths, and release techniques over time. By the end of this phase, the statue was no longer part of the mountain. It had become a mobile object, still intact, but suddenly vulnerable. From here on, every meter traveled increased the risk of damage, and every solution required balancing friction, leverage, and human endurance. How that journey was managed, whether by sliding, rolling, or something more surprising, has become the most debated question in Moai research. In the next segment, we examine the oldest and most intuitive proposal, transporting the statues horizontally on sleds and rollers. The earliest and most intuitive explanation for Moai transport is also the most familiar from other megalithic sites around the world. Move the statues horizontally using wooden sleds, rollers, ropes, and large coordinated labor teams. For decades, this model dominated academic thinking because it aligns well with basic physics and known prehistoric engineering techniques. In this theory, once a moai was lowered from the quarry, it was laid face up or face down on a wooden sledge constructed from trunks and crossbeams. Beneath the sledge, cylindrical rollers, likely made from palm wood, were placed perpendicular to the direction of travel. As the statue advanced, rollers were recycled from the back to the front, allowing continuous forward motion while keeping friction relatively low. From a mechanical standpoint, the idea is sound. Rolling friction is dramatically lower than sliding friction, meaning fewer people are needed to move the same mass. Experiments conducted in the 20th century showed that teams of a few dozen individuals could, in theory, move multi-ton stone loads using this method, assuming a steady supply of timber and well-coordinated effort. The island itself offers circumstantial support. Ancient roads radiate outward from Reino Raraku towards ceremonial platforms across Rapa Nui. These roads are relatively wide, gently graded, and in many places deliberately leveled, features consistent with sled transport. Some even contain shallow ruts, which early researchers interpreted as roller tracks worn into the surface over repeated use. However, when the model is examined more closely, complications emerge. The most serious is resource demand. Rapa Nui was never densely forested, and its largest palm species grew slowly. A sustained sled and roller operation for hundreds of statues would have required enormous quantities of straight timber, not just once, but continuously, as rollers split, wore down, or were lost. This raises a systemic question. Was statue transport a primary driver of deforestation, or did it occur during a period when forest cover was still sufficient? Some ecological models suggest the latter, that large-scale moai construction took place early, before environmental degradation intensified. Others argue the demands of transport accelerated forest loss, creating a feedback loop that eventually made the method untenable. There are also stability concerns. Transporting a tall, narrow statue horizontally concentrates stress at weak points like the neck and chin. Even slight unevenness in terrain could induce torsion, leading to fractures. Many fallen moai exhibit precisely this kind of damage, though it remains unclear whether it occurred during transport, erection, or later toppling. Finally, the sled model struggles to explain certain cultural details. Oral traditions describe the moai as walking rather than being dragged. While metaphorical language is common in oral history, it opens the door to alternative interpretations, especially when combined with the statue's forward-leaning design and narrow bases. The sled and roller theory remains plausible, especially for smaller statues or early phases of construction. But its limitations prompted researchers to ask a different question. Instead of forcing the moai to behave like cargo, what if they were designed to move upright? That idea, radical at first, leads us to the most counterintuitive and experimentally successful theory of all. In the next segment, we explore the concept of the moai that walked. Among all proposed explanations, the upright transport, or walking, theory is the one that initially sounds the most implausible. And yet, it is also the model that has performed best under controlled experimental testing. Rather than dragging a moai horizontally, this theory proposes that statues were moved standing upright, rocked side to side, and inched forward using ropes and coordinated human force. The key insight behind this model lies in the statue's geometry. Moai are not symmetrical columns. Their bases are slightly rounded, their centers of mass sit forward of center, and their bodies lean subtly toward the face. From an engineering perspective, this makes them inherently unstable, but in a controlled way. When tilted slightly, gravity assists rather than resists motion. In practice, 3 rope teams are required. 2 groups pull alternately from the left and right sides of the statue's head, while a third team stabilizes from the rear. By applying tension in a rhythmic sequence, the statue rocks from foot to foot, rotating around its lower edge and advancing incrementally. Each step moves the moai only a few centimeters, but over thousands of repetitions, kilometers become possible. Modern experiments using full-scale concrete replicas have demonstrated the feasibility of this method. With roughly 20 people, researchers were able to move a 5-ton replica forward in a controlled manner without external support structures. The motion strongly resembles a deliberate, swaying walk, lending unexpected credibility to the oral traditions describing the statues as self-moving. This method also addresses several weaknesses of the sled model. It requires far less timber, relying mainly on rope, likely made from plant fibers or bark. It minimizes bending stress on the statue's neck, since the moai remains vertical and experiences compressive forces rather than tensile ones. And it aligns naturally with the statue's forward-facing orientation toward inland communities. There are, however, constraints. Upright transport demands precise coordination. A mistimed pull or uneven ground could cause a statue to topple irreversibly. This risk likely explains why many fallen moai lie face down along ancient roads, as well as why road gradients appear carefully engineered, often sloping gently and avoiding sharp turns. Importantly, this theory reframes moai construction as a systems problem rather than a brute force one. The statues may have been designed from a start to be movable in this way, with generations of builders refining proportions through trial, failure, and tradition rather than formal calculation. Walking a moai would not have been fast. It would have been ritualized, slow, and socially visible, a communal act that reinforced hierarchy, cooperation, and belief. Transport itself may have been part of the ceremony, not merely a logistical hurdle to overcome. Yet even if a statue could walk, it still had to stop somewhere and stand permanently. In the next segment, we examine how moai were raised onto their stone platforms, where precision mattered just as much as motion. Transporting a moai across the island was only half the challenge. The final task, raising the statue onto its ceremonial platform, required even greater precision. These platforms, known as ahu, were carefully constructed stone terraces aligned with settlements and ritual spaces. A moai placed incorrectly could not simply be adjusted. Once upright, it had to remain stable for generations. From an engineering standpoint, the problem resembles controlled column erection without cranes, pulleys, or metal fasteners. The most widely supported solution involves incremental elevation using ramps, levers, and packing stones rather than a single dramatic lift. Evidence from surviving platforms suggests that the process was slow, deliberate, and highly methodical. One common reconstruction begins with the moai arriving at the ahu upright, or nearly so. A shallow earthen ramp would then be built up behind the statue, allowing it to be tipped backward slightly, while stones were packed beneath its base. Over successive cycles, the statue was raised higher as the ramp grew, each adjustment shifting the center of mass upward while keeping it within a narrow stability envelope. Levering played a crucial role. Wooden beams inserted beneath the base allowed small teams to lift one side at a time, while others placed stone shims to lock progress in place. This ratcheting method reduced the need for large synchronized lifts and minimized the risk of catastrophic failure. Once the statue reached full height, the ramp was dismantled, leaving the Moai standing on its stone pedestal. The ahu themselves were not passive foundations. Many include carefully fitted retaining walls, gravel fill for drainage, and subtly sloped surfaces that channel load inward rather than outward. This design helps prevent settling and reduces shear stress at the statue's base, especially during seismic activity or heavy rainfall. Notably, the Moai's base was often shaped only after erection. This allowed builders to custom fit the statue to the platform, ensuring full surface contact and reducing point loads. It also explains why some statues appear to lean slightly forward, a deliberate choice that enhances long-term stability by keeping the center of mass over the base. In some cases, a final element was added, a red stone topknot or pukeo, carved from a different volcanic source. These cylindrical stones, sometimes weighing several tons, introduced a new lifting challenge. The most plausible method involves rolling the pukeo up a ramp and pivoting it into place using levers, rather than hoisting it vertically. By the end of this process, the Moai was no longer a construction project. It had become an ancestor made permanent, fixed into the landscape through a combination of physics, craftsmanship, and belief. The fact that so many stood for centuries is a testament to the effectiveness of these techniques. Still, not all statues reached this final stage. Many were abandoned mid-journey or never raised at all. In the next segment, we explore why, looking at failures, fractures, and what they reveal about the limits of each construction theory. Not every Moai completed its journey. Scattered across the landscape of Rapa Nui are dozens of statues lying prone, half-buried, or fractured beyond repair. Far from undermining the engineering story, these failures are some of the most informative evidence we have. They reveal where stress accumulated, where techniques pushed material limits, and where social or environmental conditions may have intervened. From a materials perspective, the most common failure points are the neck, chin, and base. These regions experience the highest stress during both transport and erection. Horizontal transport amplifies bending forces at the neck, while upright walking concentrates compressive and shear forces at the base during each rocking step. The fracture patterns observed in fallen Moai match both scenarios, suggesting that multiple transport methods may have been used at different times or for different statue sizes. Some statues appear to have been deliberately set down and abandoned intact. These are often found near roads or partway between quarry and platform, positioned face down in what looks like a controlled resting posture. This implies that abandonment was sometimes a rational decision rather than the result of disaster, perhaps due to tool shortages, labor reallocation, political shifts, or the death of a patron lineage. Others show clear signs of catastrophic failure. Broken necks and shattered bases indicate sudden loss of balance or uneven loading. In an upright transport scenario, a single mistime pull or soft patch of ground could have caused an irreversible topple. Recovering a fallen Moai would have been extraordinarily difficult and, in many cases, likely not worth the risk. Environmental change may have played a role as well. As forest cover declined, access to rope materials, leverage beams, and soil stabilization techniques would have been reduced. This would raise the cost and risk of transport, narrowing the margin for error. Statues abandoned later in the sequence tend to be larger, suggesting increasing ambition collided with decreasing resources. Failure also reflects social dynamics. Moai construction was almost certainly competitive, with clans seeking larger or more impressive statues to honor ancestors and assert prestige. In such a system, technical limits are often tested and occasionally exceeded. A broken Moai may represent not ignorance, but overconfidence. Importantly, the presence of failures does not imply collapse during the peak of statue building. Many Moai stood successfully for centuries before later toppling during periods of conflict or ritual change. The failures we see today are frozen moments of experimentation, risk, and adaptation rather than evidence of a single fatal flaw in Rapa Nui society. Understanding where things went wrong helps narrow what could have gone right. In the next segment, we zoom out from individual statues to examine how labor, planning, and social organization made the entire system possible in the first place. The Moai were not built by isolated geniuses or through one-off feats of strength. They were the product of a sustained human system, one that combined skilled labor, shared knowledge, and social coordination over many generations. Understanding how the statues were made requires understanding how people organized themselves to make them possible. From a labor perspective, Moai construction did not require massive populations working simultaneously. Experimental archaeology suggests that quarrying, transport, and erection could each be accomplished by relatively small teams, often fewer than 50 people, provided those teams were well-trained and tightly coordinated. This makes the project far more plausible for an island society with limited population size. Work was likely specialized. Certain individuals would have developed expertise in quarrying and finishing stone, others in rope making, ramp construction, or transport coordination. These skills would be transmitted orally and through apprenticeship rather than formal instruction. Over time, efficiency would improve not through abstract theory, but through accumulated experience and ritualized practice. Timing also mattered. Construction likely occurred in bursts, aligned with seasonal cycles. Periods of agricultural surplus would free labor for monument building, while lean seasons would halt work. This episodic rhythm helps explain the uneven distribution of statues across the island and the presence of unfinished projects frozen mid-stage. Social structure played a critical role. Moai were expressions of lineage, prestige, and ancestral power. That meant mobilizing labor was not merely an economic decision, but a cultural obligation. Participation in construction may have reinforced social bonds, obligations, and hierarchies, turning engineering tasks into communal events infused with meaning. Knowledge management is often overlooked, but it is central here. The consistency of Moai proportions across centuries suggests the use of standardized design rules, possibly based on body parts, rope lengths, or tool counts rather than abstract measurements. These rules would act as embodied engineering, reducing variability and minimizing structural risk without written plans. Importantly, the system appears adaptive. As environmental conditions changed, techniques likely shifted. Smaller teams, reduced timber use, or increased reliance on upright transport could reflect learning under constraint rather than sudden societal failure. The archaeological record shows continuity, and adjustment more than abrupt collapse. Seen this way, the Moai are not anomalies. They are the visible output of a stable, knowledge-rich society operating within limits. The statues themselves are less impressive than the organizational system that produced them repeatedly, reliably, and at scale. With this broader view in place, we can now revisit the competing construction theories not as rivals, but as components of a flexible toolkit. In the next segment, we compare these models directly and explore how multiple methods may have coexisted rather than competed. By this point, it becomes clear that the question which theory is correct may be the wrong one. The archaeological, mechanical, and social evidence increasingly points toward a mixed method system rather than a single universal solution. Different Moai, built at different times and under different conditions, may have followed different paths from quarry to platform. From a technical standpoint, no single method excels at every stage. Horizontal sled transport is mechanically efficient for short distances on relatively flat terrain, especially when timber is abundant. Upright walking transport minimizes material requirements and reduces neck stress, but demands precise coordination and well-prepared roads. Lever and ramp erection techniques scale well, but depend heavily on careful sequencing and stable foundations. When these methods are viewed as modular tools rather than exclusive explanations, many inconsistencies disappear. Smaller moai may have been dragged early in the island's history, while larger statues were walked upright once builders refined proportions and coordination techniques. Short-distance movement within quarries or near Ahu sites may have used sliding or rolling even if long-distance travel relied on rocking motion. Chronology matters. Radiocarbon dating and stratigraphic evidence suggest that Moai construction evolved over centuries. Early statues are generally smaller and more conservative in design. Later examples grow larger, more stylized, and more mechanically daring. This pattern strongly suggests learning and experimentation rather than static tradition. Environmental change also shifts the balance. As forest resources declined, timber-intensive methods would become less attractive. Rope-based upright transport, which relies more on fiber than wood, would gain relative advantage. This transition does not require ecological collapse, only adaptive decision-making. Even failures fit this integrated picture. Broken statues may represent attempts to push existing methods beyond safe limits, or moments when environmental and social conditions no longer supported earlier practices. The presence of multiple failure modes aligns with the idea of multiple techniques in use. Crucially, this integrated view restores agency to the Rapa Nui people. Rather than following a rigid script, they appear to have made context-sensitive engineering choices, balancing risk, labor, symbolism, and available materials. That is exactly how complex societies tend to solve practical problems. With the technical picture now assembled, one final question remains: why did Moai construction stop at all? In the final segment, we step back from engineering and examine how ritual change, conflict, and shifting priorities brought the age of the Moai to an end without erasing the ingenuity that created them. The story of the Moai does not end with a technological failure. By the time large-scale statue construction slowed and eventually stopped, the Rapa Nui people had already demonstrated that they could quarry, move, and erect these giants reliably. The reasons the Moai era ended lie less in engineering limits and more in cultural transformation. Archaeological evidence suggests that statue carving declined before the island experienced its most severe ecological stress. This timing matters. It implies that the decision to stop building Moai was not a forced collapse under environmental pressure, but a gradual shift in priorities. The engineering system was still viable, but the social system that justified it was changing. One key transition appears to be religious. Over time, emphasis moved away from ancestor veneration embodied in Moai and toward new ritual structures and practices centered on the Birdman cult. Power became less associated with monumental permanence and more with competitive, cyclical rituals tied to leadership selection. In such a framework, investing years of labor into a single stone ancestor may no longer have made cultural sense. Conflict also played a role. Many Moai were deliberately toppled centuries after being erected, often broken at the neck in ways that suggest intentional action rather than natural collapse. These acts were likely symbolic, representing the dismantling of rival lineages' authority rather than random destruction. Importantly, toppling statues does not imply ignorance of how they were built, only that their meaning had changed. From a systems perspective, Moai construction was sustainable only as long as it reinforced social cohesion. Once statues became symbols of division rather than unity, their construction would naturally cease. Engineering follows culture, not the other way around. What remains remarkable is not that the Moai era ended, but that it lasted as long as it did. Over centuries, on one of the world's most isolated islands, a small society developed, refined, and adapted a complex set of engineering techniques using nothing but stone tools, rope, wood, and shared knowledge. The statues we see today are not puzzles left behind by a vanished people. They are the residue of choices made by a living, adaptive society responding to changing conditions. Seen through this lens, the Moai are less mysterious and more human. They reflect experimentation, failure, learning, ambition, and restraint. They show how engineering emerges naturally when social meaning demands it, and how it fades just as naturally when meaning shifts. The true lesson of Easter Island is not about lost technology. It is about how human societies mobilize knowledge under constraint, and how even the most impressive constructions are ultimately temporary expressions of what a culture chooses to value.